Good evening, everyone. Yeah. All right. Uh, Hopefully, everyone is having a good day and had a good weekend. Uh, I certainly did. So, other than that we had a dusting of snow on Friday morning where I live here, but so that's the four-letter S word, right? That we aren't allowed to say. Um, at least not in October, or shouldn't have to say, I suppose. But it all melted by noon, so it's all good. And today was a gorgeous, beautiful day, so the trees are in full bloom, and so hopefully you're all getting a chance to get out and enjoy some of this before it all goes away and is buried under a mountain of that four-letter S word stuff. So, last time we talked about kind of how cache gets moved between memory and cache, and a couple different ways to do that with direct mapping and then associative mapping. And direct mapping is, faster? Maybe? But it's hard to know, right? Because there's so many variables. Because it's dangerous because it can thrash, right? It switches back and forth between two things very, very quickly. Like every single instruction needs the opposite one, and then it is stuck in the same spot because that's how direct mapping works, right? So like we did that example with 1 and 4 where they both map into block 1. And then it just brings in each one back and forth, and that causes a lot of misses. Remember, a hit is... actually, we didn't talk about that, did we? Where is that? Oh, yeah, we'll talk about that today. And like how to figure out the hit ratio. It's pretty straightforward. Not the hit ratio. What's it called? Effective access time. Because there's access time if we get a hit, but there's also access time what happens if we get a miss. And so we'll talk about how to do that. But that'll come in a bit. But anyways, when we're thrashing back and forth, we're doing a lot of missing. So that really increases our time. So we want to avoid that, and then we brought in associative. But the problem with associative is it creates a lot more chips that we have to put in, right? Because we have to, when we go to check to see if something's in cache, we have to look at all spots, and we have to do it at the same time, right, in order to be able to increase our time complexity, right, to make it fast. Instead of looking at each one individually, we're going to look at all of them at the same time. The problem is that's a bunch more circuitry that we have to do, and there's a cost for that. Okay, so now there's one that goes in the middle, and that's called set associative. Let me get this. Yep, there we go. And then, is there a way to get this bigger? Oh yeah, there we go. Set associative. Set associative caching. What I'm going to do, I'm going to tab this in here. Actually make this a thing here like that. Go in. All right, so set associative caching. The idea here is that instead of assigning a block to a spot, what we're going to do is we're going to assign we're going to add another layer. So before we had blocks of bytes, and then we had the whole thing. And so when we did direct, we just took the block, figured out which block it is in the cache, right? And that was just done by basically doing a modulo, and then just putting it there. But instead now what we're going to do is we're going to increase this a little bit, And so instead of doing a single block, we're going to call it a set. And so it'll be a multiple different spots that it could be, but it'll be a small number. Instead of being 8 or 10 or 16, I guess it would be 8 or 16 or 32 different blocks that it could be in. It'll only be in either 2 or 4 probably. That's usually kind of how sets work. And so that way, instead of thrashing, if we get 2 of them, instead of thrashing, they'll both be able to exist there. Also, it doesn't, because it's only 4 comparisons, either we can do the circuitry like we did before with the associative, or we can remove that requirement, especially if it's only 2. It would be good to just go ahead and remove that requirement, and then if we get to a spot where it normally would be a thrashing, we'd be able to keep both of them in that set. I'll show you how that works here in a second. So that's the idea, is to take blocks and put them into sets, and then only assign a new block that's going to come into cache to a specific set, and then it's going to look for a victim to decide which one is going to get taken out. And we're going to talk a little bit about how that works. We'll do that here in a bit too. Like how to pick a victim and what to do so that we don't lose any data when we move that victim out of the victim block. Okay, hang on. Yes, that is a Minnesota Wild Cup, in case you were wondering. Maybe you saw it on a different stream as well. Okay. Where are we at? Okay. The idea is create sets of blocks and then assign each block in memory a set to go into. Pick a victim block in that set to replace. Okay, so let's go ahead and get out our handy drawing tool, and let's come up with a scenario here. Let's do a small scenario. Let's say 8 blocks and sets of 2. Okay, so let's do 8 blocks here. So this will be our cache again. And go halfway, halfway, halfway. So that's 8 blocks. Four sets. Call them 0, 1, 2, and 3. And again, and then we also have to at least consider, well, we'll come back to that in a second. So let's say over here in main memory, let's say we have say 128 blocks. Let's do a simpler version instead of doing something big like that. Let's just do 16, just so we can get an idea of how this works. That's 8. Each one is split into 2. So let's not draw those. Okay. So let's assume here, let's go ahead and pick one. let's say we're going to pick this one here, and that looks like it's about number 7. This is block 7. So what we're going to do is we're going to say we're going to have some kind of a scheme. And we can use the exact same scheme we did before. Remember what we did, but with direct, we did a modulo on it, right? And so we could do the same thing here. There are 4 sets, so we do a modulo, and we're going to put this one to set 3. Right? So we take 7 modulo 4, we get a 3 remainder of 3, and that's the correct that's what we get, and so we're going to stick it into 3. Which means, all right, also here, let's go ahead and number these here. So 0, 1, 2, 3, and that'll be what set they go into, and then it'll be 0, 1, 2, 3. Right, and we'll just continue down through those. Okay, so let's say this one goes in first. We're going to put that into either spot. The first one is available, so we'll go ahead and just stick it in there. And then, we're going to just call this X. And so it's going to take everything from here and stick it right here. But remember, we've got that address. We've got to save that address here so that we know what's there. Well, so we have to look at how big that space has to be. Well, we don't have to worry about the number of blocks here, but we do have to worry about the offset. So we need to think about how many bytes are in each block. So let's say 4 bytes to 1 block. So then when we put this in here, we need to save that information, right? So how many bits does it take to do the 4 bytes? Well, that's 2 bits. And that's in the offset. And then here we have 2 more bits for the set. And then this one has 16 blocks, so the first 2 added together have to be able to get us to 16. 16 is 2 to the 4th, so that is 2 more for the tag. All right, 2, 4, 8, 16, that's correct, 4. Okay, so this would only be 6 extra bits somewhere so that we can identify where that came from. And the offset that we would need in that address. So we would save that address there so that we would know how to find this. So each address would be 6 bits. And then each of these actually only stores the tag. It only has to store the tag. It doesn't have to store the set or the offset because that's already implied with where it's sitting. And the offset is only used once we actually access the byte itself inside of the block. Okay, so let's say then we come along and 11? So this would be 8 is 0, 9 is 1, 10 is 2, and 11 is 3. So then we would get, well, what's 11 in base 2? So let's just look at that. What's 11 in base 2? That's what, 1, 0, 1, 1? I believe that's correct. 8, 9, 10, 11. Yep. Okay. And so if then 11 is the next thing to come in, so then we would go here, and we would, instead of putting this here, which was what we would have done in direct, right? We would have copied right over the top of. Instead, there's a set here. We notice that X is in that first spot. The second spot is empty, so we're going to go ahead and put Y there. Now, what happens then if we have a 15? We go down here, we got 15. That's also in 3. Right? That's 1, 1, 1, 1. And so, and that's got Z in it. We want to bring that in. So now we have to decide which of these ones needs to go. And I'll talk about that in a minute. So let me do one more example here. And I can do this example, actually, we don't even need to write stuff in there. So let's assume that we have 8 bytes equals 1 block. Remember, each computer can do this differently. It gets to decide how it's going to do it. And depending on the system, one might be better than another. So who knows? Depends on your hardware on that system. Right, and when you increase the number of RAM, say you decide to put more RAM in your computer, right, that's memory. Well, how do you deal with that? Well, then the system has to get refigured out so that it can accommodate that, which is then, so that part of that's really important because the motherboard and or the main CPU needs to be able to understand, needs to be able to know how much, what the range is for memory, so it can devise a system so that it could use a bunch of different ones. So that's part of the reason why you want to stay inside of that range, because otherwise you can run into problems where the system wouldn't be able to effectively use the cache. Does that make sense? Okay, because it wasn't designed for it. All right, so 8 bytes. Oops, 8 bytes to 1 block. Then we're going to say cache has 16 blocks. Blocks, not blahs, blocks. In 4 sets. Sets, generally speaking, are always going to be the same size, so we don't have to worry about that. And then memory is, let's go 128 blocks. And there are no sets there, right, in the main memory. Okay, so 2 to the, or what is 128 would be 2 to the 7th. And so a set is the number of sets. There are 4 sets, which is 2 to the 2nd. And here, 8 bytes, that's 2 to the 3rd. So how many bytes do we need here? We're going to have the offset. Well, this has been consistent throughout, so this will be 3 bits. The set is 2 bits. And the tag will be 5 bits. So that means, now, we have to think about this a little bit at least. Is this a good system? Well, maybe, maybe not. It might be better to actually decrease the number of, or increase the number of sets, because the problem is our tags are really big right now compared to our number of sets. So the chance that will collide in the set is high, but our sets are 4, so if we have a collision, it's not that big of a deal. So that's one of the trade-offs, and these trade-offs are actually a big deal, and can make they can make actually a huge difference in the amount of performance. And let's talk about that. Why that's important? Because the sets are large or larger, especially compared to the size of the cache. That means that our chances of having collisions, chances of collisions go up, right, when we bring something in. So we'll bring something out incorrectly. That's the important part. But our chances of like, we decrease the chances of it being a problem because there's 4 spots there. So we might not move out the wrong one, but we did increase. It gets funny. So you're kind of doing a trade-off, and there's lots and lots of trade-offs when it comes to hardware. So I think we've already talked about some of them, but that will continue. Okay. All right. So let me talk about replacement policies. How to find a replacement. How to choose a victim. How to choose a victim. So we could just do, eeny, meeny, miny, mo, right? Like your parents probably did on your toes when you were a kid, deciding which one needed to go. But that's not a very good system, is it? Well, maybe. So this is called a replacement policy. And we probably want to say cache replacement policy, although we could use this for memory as well, and we'll talk about that in a little bit, how that works. Okay, so the first one, least recently used. That's called LRU. Big surprise there. So what this does is every time we move something into cache, every time we access something in cache, access a block in cache, any block it is, no matter what it is, we reset a timer. Okay? When accessing a block, reset the timer, and then we just look for those timers and we say which one was used last. Okay. Pro. It's a pro here. Well, that would be that this is intuitive. Right? The next thing would be, remember we went back and we talked about those localities, right? And so it says when something is accessed or a block is accessed, we're more likely to come back to that block soon. Well, in this case, we're not violating that. We're actually going to maintain a locus of a temporal locality. And that's what temporal locality. Also, I should stop for a second and say something here. I've decided to not give you guys an assignment this week. There will not be a class on Thursday. That's a scheduled day off, as far as I understand it. I don't know why, but for whatever reason, they decided to give us that day off. I think it's also MEA weekend, although that shouldn't affect a community college. I'm not sure why. But in any case, we get the day off, so there are not classes that day. And so I'm not going to give you guys an assignment this week. So I know all of you are cheering. But of course, I don't see anybody in here live, but that's okay. Anyways, so, but what are the cons here? So, okay, that tells us that's just a little bit of bookkeeping. Okay. Con. Requires a timer. And that timer takes time to reset every time you come back. Now, it's not a big deal, but maintaining timers can be problematic. It's not super problematic. It's not a really big deal because it can kind of do its own thing independently. But it's something we have to do. So requires timers. And that's probably the biggest problem, is it does require a timer, those timers. I can't think of anything else. It doesn't really necessarily reduce some threat. It generally will reduce thrashing, but right, because it's not, you have to fill a set, but it depends on if you're using set or direct or whatever. So it's still possible to have thrashing. Well, direct, no, okay. So replacement policy only applies in set associative and associative, right? Because direct, you know exactly where it's going to go, and there is no choice with what the victim is. The victim is just chosen based on where its location is. Yeah, okay. So, all right, so then the next one we see is first in, first out. So, what this means is when a block is brought in, into cache, assign it a number, assign it a sequential number, and then lowest number is the victim. I think my penmanship's getting worse. It's all right. Okay, so this has an advantage, right? Because it also has a sense of trying to prevent this thrashing business, because that thrashing thing is really, really a problem. So it's going to try to prevent that by saying whatever's been in cache the longest is what's going to go out first. Right, first in, first out. Or FIFO. F-I-F-O. otherwise known as a Q. So what are the pros here? This is also pretty intuitive. It's easy to understand. Does it keep temporal locality? It does. So we see temporal, right? This is a temporal locality is maintained. Is it maintained as well as the pro, though? No, because kind of. Because remember, it's first in, first out. When a block is brought into cache, it's assigned a sequential number. And then the lowest is the victim. Right, because that number continues to go up. Okay, that's great. But how about if we just accessed it? So it came in first, and then another one came into the set. So let's say our set is only a size 2. Or it's a size 4. And then 3 other ones came in, and those have been accessed. But then we jump back and access the first one that came in first. It doesn't have a sense of that. Okay? So one of the cons is problem accessing old data. When I say old, it's just been there less or longer than newer stuff. So what that does is it changes the sequence, right? But there's another one here. This is actually faster than LRU. Because we don't have to do the timers, and we don't have to compare timers, right? We just have some number that we can just quickly check between the 2 or 4 or however many there are, and we can quickly decide which one's the victim. But it's not as good, but it is faster. Well, now we're going to come to the fastest of all of them. Random. Select one at random. Pro. This is the fastest way to do it. And, actually, let me go down here. This has no overhead. We don't have to set any bits. We don't have to do any clock. We don't have to do anything. So we have to pick one, just grab it, throw it away. So here's the interesting thing. How does it perform? So this is the fastest to pick, to decide. It's also faster to copy things in because we don't have to worry about a clock or an integer. But this one is the most prone to thrashing. Now, what does that mean? Well, here's the thing though, because it's random, let's say you have 2 in there, and if you pick the first one, you're going to get a thrashing situation, right? Because you're going to need that one in a second. Of course, we don't know, right? Because we can't look ahead. we don't look ahead when we do these things, because we want them to just be fast. So we're not going to try to do any kind of anticipation. There are ways to do that. I'm not going to get into it. So if we pick 1 to get rid of it, we're going to need to access that just in a second. So we need to pick 2, and there's only 2 there. If we pick the second one, it's not going to thrash. So if we pick the first one, so then we pick another one. Now 1 again will cause us to thrash, but 2 won't. So it's 50-50, and each time it's 50-50, rather, which one's going to get accessed next. And so what will happen is it might thrash for a couple times, but then it'll stop because we'll actually get it. We'll actually accidentally pick it right. So thrashing doesn't continue for a long period of time, most of the time, right? Because you could pick the wrong one every single time. You know, the odds of that happening are really low, but it's possible. And if that happens, well, then that's a bummer. Okay. So those are the 3 different ways that we can do replacement. All right. So now let's talk a little bit about let's talk about E. So effective. Let me do this with a get a bigger one. All right, let me actually do a text thing. $36. Called EIT. Okay. So this has a formula. Odds. Oh, let me. H equals odds of getting a hit. Access sub C. Turn it back off. Equals time to access cache. And then we'll do let's do M equals odds of getting a miss, and this is 1 minus H. It's always going to be 1 minus H. Put some spaces in there, make it look a little nicer. And then access subscript M. Okay, so what's our formula look like? Oops. EAT equals H times access C plus, oops, plus M times access M. I could say this is 1 minus H. It's fine, doesn't really matter. So here's the thing, though. When we look at access C, how quick is that? How fast is it to access cache? Let me swing back to this. Let me go back to that page here in the book here. Back a few more spots here. Suppose I could have opened up. All right, so let's say we're talking about L1 cache here. It's 3 to 8 nanoseconds. How about main memory? 10 to 70 nanoseconds. Okay, it's twice as fast, I guess, about. Maybe more. 2 to 10 times faster. 2 to 9, maybe somewhere in there. Okay. Is it important to get our hit rate as high as possible? Yeah. The higher the hit rate, because remember, these are inverse of each other, right? So 1 minus H is going to be the M. So this will be a fraction, either a fraction or a decimal. And so will this. So if we can guarantee hits, that just makes it, it doesn't matter how slow our cache is compared to our memory. If it's only twice as fast, it doesn't matter. We know it's going to be faster. But let's say it's just barely faster. But it doesn't matter. If we can increase our hit rate, that will increase our effective access time. So let's do an example. Just because we can. So let's say our H, okay, let's say H equals, say 0.9. And I'm just going to call it AC. Come on. A sub C. Let's say that equals, what, 6 nanoseconds? And then we say, then M would be equal to 0.1. And access main memory. Let's go, what was the range on that? 10 to 70. So let's say that's 20. So that's relatively fast. All right, so what we're going to do is we're going to say 0.9 times 6 nanoseconds plus 0.1 times 20 nanoseconds. Let's put the NS on that. Okay, so this would be 0.54 nanoseconds plus 2, right? Yeah, 2 nanoseconds. And I didn't do that right either, did I? Nope. 5.4. This equals 7.4 nanoseconds. And so what this does is it because most of the time, 90% of the time, we're going to be at 6 nanoseconds. But 10% of the time, we're going to be at 20. So what we're doing is we're kind of we're amortizing. Actually, that's not the right word either. We're kind of averaging it out. We're spreading out the misses over the hits to kind of try to even everything out. We could also say this is how much. This is the access time. The effective access time is really what's important in a system, right? Because your cache could be phenomenally fast, but if your hit rate is low, it doesn't matter. So, and so we could look at another one where the cache was, say, 7, but the hit rate was 99%. Then the main memory's access time could be really slow. Comparatively, it could be 70. Well, let's do that. Hit rate equals 0.99. AC equals 7 nanoseconds. So M equals 0.01. And AM equals, let's say it's 70 nanoseconds. So let's see which one's faster. 0.99 times 7 plus 0.01 times 70. These are nanoseconds. Okay, on this side, the math is easy, right? 0.7 nanoseconds. And this one here, bring up a calculator. 0.99 times 7. 6.93 nanoseconds. Well, let's bring this up and let's double check my math. 0.7 nanoseconds. Okay, so I add these together. I get 7.63 nanoseconds. So it looks like this one's just a hair faster. But not by much. It's pretty close. Right? If we had this at 6.5, if we lowered either of these two numbers, we could get it down. So I'll leave it to you for you guys to play around with that. Okay. Now, so we've done access time. We've done this replacement thing, right? We've also talked about one more type of caching. But what do we do when we replace something? And this goes for all three systems. Yeah, let me do this in writing again. Well, geez. Cache write policy. What to do when when a block in cache is modified. So a dirty block is a modified block in cache. And again, we could extend the idea of, we could talk about main memory and storage in the exact same way, right? It's going to have similar policies at that next level, bigger. Although we bring in some other things as well. Okay. So there's two different ways to do this. Write through. And this says when a block changes in cache, change it in main memory. So if we write something in cache, we also have to write it into main memory. A little bit slower than the next one here. The next one is called write back. When a dirty block, again a modified block in cache, when a dirty block is selected as a victim, write it to main memory. So what we're going to do, right, in the second version is we're going to just note it somewhere that it's changed. Or when we get to the end, when it's time to take a victim out, right, that means it's going to be taken out of cache. Then we're going to decide at that point, we're going to check the memory. And so we're going to only have that overhead once to writing, but we do have to check to see if it's different. So we'll have to do that check, and then we'll go ahead and make that change. The write-through policy means that we're always going to make that write out to memory. But here's the cool part: is we can actually create a little piece of software, a little not inside the CPU, but actually at the cache, in the cache. So we can have a little processor in there that just goes ahead and does that work, so that the processor doesn't have to. So we can create some hardware right in the cache to do this. And so this is all requires circuitry. Both cases actually require some amount of circuitry. So one slows down the writing it slows down when you're going to bring something in, which is kind of a problem, right? Because that is usually when that happens, that's the CPU is actually waiting for that data. On a write-through policy, we can do it while the CPU is working about other things. So one is more effort, the other one is less effort. So that's good, which also requires less power, less electricity, not by much, just a very little bit difference. But sometimes every little bit helps, especially when we get to the extremities of when we're pushing how much energy that we're using, how much power, electricity that we're using. And I see that becomes a problem, right? On your cell phone, maybe it dies too fast, right? So, we could either use it less. Come on, that's just outside the realm of possibilities, right? Instead, we demand that the power usage on it goes down. The interesting thing on a CPU, on a phone is the number one thing to drain your battery is your screen. It has nothing to do with processing. So the best way is to turn the screen off. But then you can't use it, or makes it much more difficult. So there it is. That's that. Okay. Oh, actually, this is actually kind of cool. I'm just going to talk about these. I'm not going to write any notes for them. There's sometimes on certain computers, they'll have a data cache. So they'll have a cache just for data. So just for your variables or things like that you're going to be saving. And so we know that, so then that might use this write back policy. And then we have instructions, and those instructions are never allowed to be changed. Or we can make that we can have that policy. But it turns out that actually you can change instructions as you go. Be careful if you want to try to do that, but be very, very careful. So it's not recommended for people who are new to doing assembly. It is possible to do though, because it's all data. So anyways, you can have instruction cache that just the instructions. That makes it a little easier with your counters and things like that. So it also means, right, you don't have to have a write back policy because, say, in instructions, you're never going to change them. You could just have that policy. You won't allow it to be changed. And maybe that's a good policy, maybe it's not. Okay, another thing you can do is you can have a victim cache so that when a victim is created, the victim will simply go out to this victim cache, and in the victim cache, then that's going to do the write back out of the victim cache space. So you just simply write it into the victim cache, and then it will, in the victim cache, there's a little processor in there that's going to write that back out to memory, and then forget. So it's really interesting because the cache never it doesn't. This is true for storage and for memory and everything all the way down the line. When you deallocate memory for something, like when you say, okay, we're done with this. Say we're using this victim cache, so we, a block gets overwritten, and so then before that happens, we move it out to our victim cache to allow our little processor in there, a little victim processor. That's going to take it and bring it out to main memory again to a write back policy. But then it has to forget that thing is in there. And it can do that. There's various different ways to do that. But it doesn't actually change the memory, because that takes energy. And so we just leave it alone. So those flip-flops that are sitting in there, we're just going to say, forget it. Just keep doing your thing. We're not going to change anything. We're not going to give it an impulse to tell it to switch, because it's just a waste of energy. We're just going to let it be whatever it is currently. Which means sometimes you can go back and look at things that aren't, especially when it comes to storage. And when you hear about, like, the FBI being able to crack into somebody, even though they've reformatted it, right? They reformatted their hard drive, but the vast majority of that hard drive nothing changed. It just forgot where those things were. And so the forensics, you can actually do digital forensics on that and go in and actually see what those values were in each of those places. And so they can actually do some retrieval. It's really, really neat stuff. The vast majority of you will never use that. I did get to see some of it, but I didn't study it in real depth. But it's pretty cool. Okay, last topic for the day. Virtual memory. I know I've covered a lot of things, but I wanted to finish Chapter 6 today. And I think we've covered these things in fairly good detail. Okay, so virtual memory is when you use storage. Remember, storage is probably a hard drive, so read that as a hard drive. So SS, solid state drive, or high density disk. I think that's what that stands for. Use storage as memory. Remember, it's not as fast, is it? In fact, it's way slower. SSD is not as much, not a ton slower, but the hard drive for sure, it's like 1,000 times slower. Okay, so how can we use that as memory? So what happens is, there's two different ways to do this. And if you want to go into some more detail, I'm not going to go into it. I think it's something more for an operating systems class. So, but I'm going to introduce these two things, okay? One is paging. And so that says, so what it does is it says split data into same size. So same size pages. And so what happens then is it's going to put pages as they're needed into main memory. And then it's going to switch out those pages based on it. There's a lot of different systems to do it. And in fact, LRU and FIFO and random, those are still legitimate ways to do paging, right? Because you have to pick a victim page instead of a victim block. So what paging does is it takes this program and it breaks it down into smaller chunks called pages. And each of those pages gets brought into memory as needed. And there's a way, it's possible, right, that we can kind of look forward on those pages to see when we're going to have to access them. And so it tries to, at least, tries to do that, to bring things in as they're needed. The other one is called segmentation. So this says split the data into variable size segments. Right, so one of the problems with paging is, say your paging is 1 kilobyte. So you're going to bring in 1 kilobyte at a time into your memory. Makes sense. But what happens if you have 1 kilobyte, or you have a program or data that's 10 kilobytes plus 1 byte? So now you have a whole page that's virtually empty, has 1 kilobyte in it. Enter segmentation. Right? And we could use them in conjunction. There are ways to do that, but we're not going to worry about that either. So segmentation says split it into sizes that make sense. So it might make, it might do the same thing as pages, or it might just simply say, we're going to split, we're just going to average it out, or figure, it's going to figure it out. It decides on the size of the segments. Segments mean you're going to get effective size of things coming into memory. You're not going to waste memory space, but there's more overhead because you have to figure out what the size of each segment is, because each segment's different size, and it's got to deal with all of those kinds of things. Whereas in paging, it just says, go, no problem. Okay. Yeah, the book defines something called internal fragmentation. I'm just going to introduce this because it's a general principle. In the old days, in the old days, when I was your guys' age, back when the Earth was still young, it's not true. But in any case, back in the old days, let's say in the 90s, one of the things you had to do with a computer, if you used it a lot, especially if you were adding data onto it and taking things off and doing that kind of stuff, is you had to do something called defragmentation. And it's still not a horrible idea to do now. So what happens is when a piece of data gets stored onto your hard drive, on an SSD drive, it's completely useless. It doesn't matter. You never need to do it. But on hard drives, because of the way they spin, you wanted your program to be in sections together, but it didn't always get allocated that way. So sometimes it would be spread out across the different drives in different places. And so what it would do is that defragmentation was to try to bring it together. And the reason it does that is so that it can page easier and segment easier, because all the data is in one place. Now, sometimes a program is easily split up into pages, and so in that case, then the pages really don't matter where they are. It could be anywhere. Same with segments. So that's just a thought there. There's this defragmentation. That's the reason why you need to do that. And it's not because of virtual memory necessarily, but it comes with any kind of a program. You're going to bring it in the same exact way, probably. But yeah, the virtual memory, there's different strategies for it. Like I said, that's more of a operating systems strategy. We're not going to worry about it here. We're just going to kind of gloss over this part of the section. Yeah, there's some stuff at the end of the chapter here that I think is really fascinating and good. I'm not going to quiz on it or test on it, but it's still a really good idea to use that and look at it. Kind of how memory management actually works on a bigger scale. Oh, we should talk about schedule for a second. Where's my schedule here? I have it around here somewhere. Okay. Oh, geez. It's right here in front of me, in front of my face. Okay, so no class this week. All right, so we'll do assignment 7 this week on Friday, or next week on Friday, I mean, and that'll be over chapter 6. And then we'll do exam 2 on the same date that it says we're supposed to do it, so it would be like the 3rd or something of November. 4th. The 4th of November. So assignment 7 will be not this Friday, but will be October 28th. And that'll be chapter 6, which is all the stuff on memory that we've talked about both last week and this week. So I think we did it Wednesday and Thursday of last week and then today. But that'll include also way back to 4. So what is that? What is it? Maria, instruction, formatting, and pipelining, and instruction types. What's the name of the chapter even? Instruction set architectures. So Maria, kind of how Maria works, and then instruction sets and how those work, and then memory. And then we're going to go here. My mouse. Exam II. November 4th. That'll be chapters 4 through 6. And that'll give us a few more weeks to go here. We'll see how things go. I think originally I had 13 assignments. I don't think we're going to get to 13, especially if we skip one this week, and I think it's fair to do that. So, anyways, when will I get to 10? I might delete a couple as well later, based on the fact that we're going to do some programming stuff. So, but for the most part here is I'm going to continue going through the book here. We only really have, I guess we've got 7, 8, 9, 10, 11. So we have 5 more chapters, although some of those chapters are kind of small-ish. So we'll like 8 isn't real big, 10 isn't real big, but we'll go through the rest of these. And I'll wait for time. Okay, so the next one is input-output, and we're going to talk about how that works in the next one. Including all the RAID levels. Yes. I love RAID. It's really neat. stuff. Then we're going to talk about software systems, a little bit about operating systems and how they work. Just real introduction level for the most part. That's why it's small, because it gives you an introduction whether you want to study that later. Alternative architectures, so RISC machines, Flynn's taxonomy, parallel processors, quantum computing. That's a tough one. Then we'll talk about, in Chapter 10, we'll talk about embedded systems. Like, that would be like anything that's inside of something else. So, hopefully my audio was decent, because I haven't had my camera or my microphone up here to my face. I had it across my desk. So, and then Chapter 11 is some performance measurements and analysis. And we'll look at some of that a little bit anyways. And then we're going to wrap that stuff up. So I want to get through the rest of the material that we're going to cover. And then what we'll do is we'll launch into just doing some assembly level programming in Marie. So that's kind of my idea, so you get an idea of what's going on. And that's why, if you notice, there was a lot of blank spaces on the schedule at the end. And so some of those will be either me live coding and working on stuff, or we'll just not do it. So it depends on how. I'll get some feedback from you guys on how you want to do that. So, and we'll talk about that when we get later in the semester. That'll be a couple weeks from now. Or I could intersperse some Marie, but I think I'd rather just get through the text first, and then we can concentrate on programming, which is what we're all here to do anyways, right? So, all right, that's all I've got for today. I will talk to you in a couple days on Wednesday.